So the topic of today's lecture is development of rapid methods for relaxation time mapping and motion estimation using magnetic resonance imaging. The outline of this lecture is that in the first section I will present rapid acquisition schemes for relaxation time mapping, and then there is a method for processing phased array data for rapid relaxation time mapping. And in the third section of this lecture, I will talk about a rapid motion estimation scheme. So in the first part, let's first look at the longitudinal magnetization recovery. On the y-axis, the z component of the magnetization is shown, and with time, if let's suppose the magnetization is inverted, so with time it tends to behave like an exponential curve. So for fat and white matter and gray matter and CSF in the brain, we have different relaxation timings, and all the tissues, they relax as to their initial amount of Z magnetization with this scheme. So we can see that the fastest among the recovery is CSF, and the slowest is the fat tissue. And what the motivation for the rapid mapping scheme is that measurement of the spin lattice relaxation time constant T1 can provide important insights into pathological processes in the human brain, such as multiple sclerosis or hepatic encephalopathy. Actually, the acquisition times they tend to be long, and therefore reductions in acquisition time are desirable to attain routine clinical objectives. And there's a sequence, it is known as taper T1 mapping with partial inversion recovery, and it is basically a look locker based multi-shot sequence which is used for fast multi-slice T1 imaging. I will show in the next slide about its working. And taper is capable of multi-point in vivo imaging with high spatial resolution, 1 millimeter in plane to be exact, and it uses interleaved slices and time points acquisition scheme for acquiring the data. So this is the basic sampling scheme for which taper uses, and this is the inversion recovery curve schematically shown. And first I want to emphasize here, let's say how this inversion recovery curve is sampled. So let's suppose we have 5 slices, and for each of the slice 5 time points are to be acquired. So it works like that: the first time point of every slice, it is acquired on the inversion recovery curve in from this time period to this time period. And after that, second time point is sampled for all of the slices, and then third, and then fourth, and then fifth. So that's how the whole inversion recovery curve is sampled for 5 slices and 5 time points. And if you look at on the right side, this is actually the sequence diagram of the taper sequence. Here the separation of the 90-degree and 180-degree pulses is actually not shown to scale, but this is a time separation between these two pulses. And following the application of 90-degree non-selective RF pulse, the transverse magnetization thus created dephases during the long delay period tau. After this delay time, a non-selective 180-degree pulse inverts all recovered magnetization, and any residual transverse magnetization is spoiled by means of a large crusher gradient. The inverted magnetization is sampled in the following way. The most peripheral line in K-space is acquired by the application of a single slice selective alpha pulse. The alpha pulse excitation module is repeated for the next slice. This you can see inside these brackets. And after that, the next time point is sampled by repeating the same module. This you can see by the brackets shown here. And after that, for the next line, the whole module is repeated again, and this module contains the 90-degree and 180-degree pulse also. And this loop actually ensures the acquisition of multiple time points. Following acquisition of the required number of time points and slices, 90-degree and 180-degree pulse combination is applied again, and the next line is acquired in an identical manner as I explained before. So what are the advantages of rapid acquisition? If you can save time, let's say on the left side diagram, it is shown that you have acquired the 5 slices and 5 time points quickly, and you save, let's say, this time period. In this time period, you can acquire more time points, and then the acquisition scheme will look like this. You see that time point 6, 7, and 8 can be fitted also in this saved time period. So later on when fitting will be performed using the data points, it will give you more accuracy and precision in the data fitting. And there can be another advantage, which is if you save time like this, then you can acquire actually more slices and keeping the data points with the same as you have before. So here you have acquired 10 slices, but you have acquired only 4 time points, or you can acquire 5 also. This is just a schematic representation. So that's how you can basically go for whole brain coverage. And the scheme actually which is used for the rapid acquisition is that you are sampling the whole K space, and you're let's say you first I want to tell about the division of the K space. Let's assume on the inversion recovery curve you are here and you are sampling the full K space here. So first you acquired the first line, and then you do not acquire the second line, and then you acquire the third line and not the fourth one. But in this central region of the K space, you are sampling completely all the K space lines, and when again you go to the periphery, then again you are subsampling the periphery by a factor of 1. And When you go to the next time point, you are just missing the line numbers which you have acquired before. So here you have missed the first line, you have acquired the second line, you have missed the third line, and then you acquired the fourth line, and so on. And actually the scheme is that if the first line is missing at, let's say, time point n, then you can reconstruct this case-based line by interpolating the line for line number 1 from case-based time point n minus 1 and case-based time point n plus 1. So you use this case-based line and this case-based line, you interpolate it, and this used at the first line in the time point n. So that's how you completely fill the missing case-based